Good morning to all. This is Dr. S. Arnath Babu, Assistant Professor of Physics, Annamacharya Institute of Technology and Sciences, Rajanpet. Today, I discuss the dielectric properties of the materials. So, first we discuss the fundamental definitions of the dielectric materials. The first one, electric dipole. A dipole is defined as a pair of two equal and opposite charges q and minus q separated by a distance small r. So here we are taking two equal and opposite charges minus q and plus q. These two charges are kept at a small distance small r. Then this arrangement is called electric dipole. Next, dipole moment. Dipole moment is equal to the product of one of the charges and the separation between two charges. So here the dipole moment is denoted by mu. Mu is equal to q into r. Q is the charge, r is the distance between two charges. Here we know that the distance between two equal and opposite charges is taken as small r. So the dipole moment mu is equal to q into r. SI unit of dipole moment is coulomb into meter. Another unit is debye. Here 1 debye is equal to 3.3 into 10 power minus 30 coulomb into meter. Next one, permittivity. Permittivity represents the easily polarizable nature of the dielectric medium. Permittivity of dielectric is denoted by epsilon and permittivity of free space is denoted by epsilon naught, where epsilon naught value is equal to 8.854 into 10 power minus 12 farad per meter. Here if you take the any one capacitor plates in any one capacitor, and we take two capacitor plates and connecting to the battery, positive terminal and negative terminal, then the positive charge is induced on the one capacitor plate and the negative charge is induced on the other capacitor plate. So here the electric lines of forces are passing from positive charged plate to negative charged plate. So here in the if you keep any medium or vacuum, then electric lines of forces are passing through that medium. Then the ability of the material to allow the electric lines of forces is also called permittivity of the material. Next, dielectric constant or relative permittivity. The ratio of permittivity of medium to permittivity of free space is called dielectric constant. Dielectric constant is denoted by epsilon r. So epsilon r is equal to epsilon by epsilon naught, where epsilon is the permittivity of material, epsilon naught is permittivity of the vacuum or free space or air. Consider a capacitor with air as medium having charge capital Q on its plates are separated by a distance small d. Let area of cross section of the plate is capital A, V naught is the potential difference and capital E naught is the applied electric field across the plates. So here we are observing that we are taking one capacitor. Capacitor has two plates. These two plates are connected to the battery. So positive terminal is connecting to one capacitor plate. Negative terminal of battery is also connected to another plate. Then one plate near the positive charge, near the positive terminal of battery on the capacitor plate, positive charge is induced. In other side, that is near to the negative terminal of battery, the negative charge is induced. Then the potential electric field is applied. Electric field is applied from positive charged capacitor plate to negative charged capacitor plate, that is taken as E naught. Next, potential difference is formed between two capacitor plates, that is taken as V naught. The distance between two capacitor plates is taken as small d. Area of the capacitor plate is taken as capital A. Next, capacity of capacitor when air is between two capacitor plates, that is denoted by C naught. C naught is equal to capital Q by capital V naught, and C naught is also equal to capital A epsilon naught by D. When the dielectric is introduced into the capacitor, opposite charges are induced on the two dielectric faces which are close to the charged plates. These induced positive and negative charges act as dipoles and it has net dipole moment. This phenomenon is dielectric polarization. Due to the dipoles, the resultant potential difference decreases so that capacity increases. Due to polarization, the polarization electric field EP is induced in opposite direction to the applied field E naught. Resultant electric field E is equal to E naught minus EP. So where we discussed that, where we are taking one capacitor and we are keeping one dielectric material between two capacitor plates. Then what happened? The electric lines are penetrating through the dielectric material. Then the dielectric material is polarized. Next, the dipoles are formed, produced in the dielectric material. So, in opposite direction to applied electric field, polarization electric field EP is formed. Then the resultant electric field capital E is equal to E naught minus EP. Let Vd is potential difference across capacitor plates. Then capacity is given by Cd is equal to Q by Vd, where Cd is the capacity of capacitor when dielectric material is placed between two capacitor plates. Cd is equal to capital Q by Vd. Vd is the potential difference when dielectric material is between two capacitor plates. And another formula is Cd is equal to epsilon A by D. Epsilon is the permittivity of the dielectric material. The ratio of capacity of capacitor with dielectric to capacity of capacitor without dielectric is called dielectric constant. Epsilon R is equal to Cd by C naught. Epsilon R is equal to Q by Vd by Q by V naught, where Cd is written as Q by Vd. C naught is also written as Q by V naught, where Q gets cancelled. Then epsilon R is equal to V naught by Vd. Dielectric constant is defined as the ratio between potential across the plates with air medium to the potential difference with dielectric material. Next, epsilon R, dielectric constant or relative permittivity. Epsilon R is equal to E naught by E, where E naught is the electric field with air between two capacitor plates. Next, capital E is the resultant electric field when dielectric material is between two capacitor plates. So dielectric constant is also defined as the ratio between electric field with air medium to resultant electric field with dielectric medium. Epsilon R is equal to Cd by C naught. Next, epsilon R is equal to epsilon A by D divided by epsilon A by D, where the capacity of capacitor with the dielectric Cd is written as epsilon A by D divided by C naught is written as epsilon A by D. Next, epsilon R is equal to epsilon by epsilon naught. Dielectric constant has no units. This is only number. Next, dielectric polarization. Polarization is defined as the dipole moment per unit volume. Let capital N is the number of molecules per unit volume and mu is a dipole moment of molecule. Then polarization vector capital P is given as capital P is equal to capital N into mu. SI unit of dielectric polarization is Coulomb per meter square, that is denoted as capital C by small m square. Dielectric susceptibility chi. It measures the amount of polarization produced in a dielectric by applied electric field. polarization is proportional to the product of permittivity of free space epsilon naught and electric field capital A, where you can write as capital P proportional to epsilon naught into E. Capital P is equal to chi epsilon naught into A, where we are replacing proportionality with equal symbol, and then we write extra another product, that is chi susceptibility, where dielectric susceptibility chi is equal to capital P by epsilon naught E. Next, electric flux density or electric displacement, that is denoted by capital D. The total number of electric lines of force passing through unit area of cross section of dielectric is called electric displacement, that is also known as electric flux density. Consider a dielectric in an electric field capital A. The electric lines of force passing through dielectric and it can be polarized. Electric displacement capital D is proportional to the applied electric field capital A. So capital D is proportional to capital A. Capital D is equal to proportionality constant epsilon into capital A, where epsilon is permittivity of dielectric material, capital E is the electric field. Relation between dielectric constant and susceptibility. But electric displacement capital D is also related to electric field capital E by capital D is equal to epsilon naught E plus P. From equations 1 and 2, epsilon E is equal to epsilon E plus P, where epsilon or permittivity of material is written as product of epsilon naught and epsilon r. So we can write as epsilon naught into epsilon r into capital E is equal to epsilon naught into capital E plus capital P, where polarization vector or polarization capital P is equal to epsilon naught epsilon r capital E minus epsilon naught into E, where polarization vector capital P is equal to epsilon naught into E is taken into common, then epsilon r minus 1. Next, send this epsilon naught into E into left side, then capital P by epsilon naught into E is equal to epsilon r minus 1. So from definition, susceptibility chi is equal to capital P by epsilon naught into E. From equation 4 and 5, we can write as susceptibility chi is equal to dielectric constant epsilon r minus 1, where dielectric polarizability alpha. Dielectric polarizability is denoted by alpha. Dielectric polarizability is defined as the net dipole moment per unit applied electric field. Net dipole moment is proportional to the applied electric field. So net dipole moment mu is proportional to capital E, applied electric field. Next, mu is equal to proportionality constant alpha into E, where proportionality constant alpha is called dielectric polarizability, so that polarizability alpha is equal to mu by E. SI unit of polarizability is equal to farad into meter square. So polarization capital P is equal to capital N into mu, where N is the number of atoms per unit volume. Mu is the polarizability, where P is equal to capital N alpha into E.